Hi and welcome. This is Lorenzo Torricelli from the University of Parma, and this video is a short introduction to financial models based on the logistic distribution. I have some slides with some theoretical background material, and then we will jump to the mathematical code where we can see the logistic distribution and the associated processes in action. The talk is based on this process, on this paper, Additive Logistic Processes in Option Pricing, which is available at SSRN and will be shortly updated. So what is the idea to generate logistic security underlying martingale processes? The idea is to start from valuation equations. So we start from no arbitrage option functionals, a call option functionals which is supported on the real line, and a function for valuing the merit put, so the max payoff, which is supported on the positive reals. So S and B here, so you have an excess, a normalized moneyness here, and two term functions appearing S and B, which describe the intertemporal behavior of the options prices and of the underlying price distribution as well. So long as S and B, these terms function, are 0 and 0, are increasing, and B is bounded, you can verify that C and M are decreasing in strike, convex in strike, and increasing in maturity, which is all you need to establish that this formula are arbitrary free. Once you've done that, you just take the derivative with respect to K, and you generate, and then by the famous remark by Britton and Litzenberger, you can obtain the implied security price distribution. What are the CDF in particular? What are they? For the real valued underlying coming from the log sum exponential functions is just a logistic function. For the positive price process coming from the merit put positive valuation equation, you have the so-called Dagum distribution, which after a log transform is seen to be nothing else that skew logistics distribution. So another form of the logistic distribution with a distortion power here appearing, which gives you the negative skewness. So these are the log returns of the positive price process coming from the merit put valuation. What else? Those distributions are infinitely divisible. So those of you familiar with theory of Levy process might wonder, then can we do then with a Levy process associated to them? Well, in principle we could, but it turns out that this is not the right thing to do. It would not support such a process, the evaluation formula we started with. So we have to do something else. We have to consider this infinitely divisible as a time family. And once you've done that, you can apply a theorem which grants the existence of an additive process, provided that the law that you have chosen, that you're starting from, satisfies some technical assumption on the Levy structure, which in our case turns out to be the case, and that's all we need to verify: the existence of an additive process, which means stochastically continuous with independent increments, supporting the implied price distribution, underlying security distribution, which in turn determines the formula we started with. An additive process is what you get if you relax the time homogeneity from a Levy process. Okay, and also it turns out that these processes in our specific case are pure jump. These are technical details on the Levy structure of the log returns of the positive model and the returns in the models which has logistic distribution. So log logistic, skew logistic, and logistic return for the processes. Once you've done that, we are basically in business, because the bit missing is that those processes must be martingales, and they naturally are. Why? Because we obtain distribution starting, so a class of time-dependent distribution, starting from no arbitrary valuation from them in the first place. So you can verify this mathematically, but financially, the reason is what I just mentioned. We call the two models the CPDA model, conjugate power Dagum additive, and the second model, it's a logistic additive model, which has, in addition, a self-similar specification, taking the term function S to be sigma th. Now, for numerical test, I'll take B, so the bounded term structure in the CPDA model, to be something which look like the self-similar specification in the SSLA in the logistic model when time is small, or something of this sort. If you do the Taylor expansion, you see that. Okay, so we have a model with all these. I'll let you go through them. These good desirable properties, which supports some very simple pricing formula, which is basically what we are starting input. Going through the code, I hope you don't mind too much the terrible coloring. So what I'm done here is I'm implementing some formula from our paper. And so here I have the specification for the term structure. I have the formula. I implemented the formula for the option, CPDA and SSLA vanilla options, pots and calls. And also I have the distribution, logistic and skew logistic. So log returns for the CPDA, returns for the SSLA. So the formula and their instantiation in terms of the term function. And there's these expressions for the cumulant term structure for those models, which can be expressed as functions of the Riemann zeta and the polygamma function. So the first test I'm doing is a density comparison. I want to compare the density of the logistic pricing word with the standard normal models, Black-Scholes and Bachelier. What we have, so I'm comparing, of course, the log returns of the CPDA, the Dagum positive model, log returns are skew logistic, versus the normal. So the log returns in the Black-Scholes models, which are normal with variance sigma squared t and mean minus sigma squared t over 2. So I just drift adjusted in order to when you exponentiate, you have a martingale relationship. So what we see here is that as time progresses, the normal distribution just, there's a variance increase, of course, and there's a bit of a location shift, backward location shift, but the shape does not change, which is in contrast. When you consider CPDA model, what you see is that the skewness, so the shape of the distribution, changes with t, and the left tail becomes progressively heavier than the right one. So you see, this of course does not happen in the normal world, and this is a remarkable fact which has implications for a martingale relation. When you look, instead of the comparison of the normal and logistic distribution, once you variance match them, so in the left plot, I haven't done variance matching. Here in the right-hand side, it's much easier. I did do that. And you see that, in fact, the distribution are quite similar, but kurtosis can be clearly appreciated. Okay, so the blue line is the logistic word, and the purple line is the normal word, the normal plot. So you see the double crossing here, which indicates skewness for the logistic distribution, heavier tails, and more peaked distribution around the mode. So I have what I also have is cumulant term structure. I am plotting the cumulants as a function of time for blue, again, the logistic model, and I am benchmarking again a linear evolution of the term structure, which is typical for homogeneous models, so Levy models. And what I observe is that I can generate much more flexible shapes, in particular an exploding variance here, and a short-term, very steep increase of the skewness. Okay, so this is not really Black-Scholes. These are not Black-Scholes. These are homogeneous models. I should write here. Black-Scholes is symmetric, so I should the line does not exist. Anyway, so you see that there's a is a high rate of increase of negative skewness, which indicates possibly might be connected with a steep short-term volatility skew because of asymmetry of the distribution. Also, the kurtosis is a very interesting flexible shape. Moving on, so for the logistic, these are plots for the CPDA model, so log returns in the positive model. The returns in the real valued model, the SSLA models, have show a similar pattern for the variance and a constant kurtosis, which is a known fact for the logistic distribution. It does not depend on scale, and therefore it does not depend on the scale function in that case. So finally, implied volatility to the surface. This is just an implied volatility finder, normal and log normal. I have two models which just produces for the SSLA and CPDA models volatility surfaces for some given model inputs. I have 225 here, 225 options. I do a speed test and I see that this is very fast because the option formula are explicit, known in closed form, and much simpler than even than Black-Scholes, by the way, I should mention. When we look at the volatility surface, we see that we have for some an implied volatility skew is present in the skewed distribution, the positive one, the CPDA model. Okay, so the log returns are skewed, and this is reflected in an implied volatility skew. As you can see, the deep in the money options come at a higher premium compared to their out of the money, deep out of the money counterparts. This is you still have a smile in the logistic distribution because of kurtosis, but there is no skew because the logistic distribution is symmetric. And besides, you see that the model parameters also impact the volatility term structure in a similar way. Two parameters are not very orthogonal. So maybe there is some work with something can be improved in the parameterization, which I have chosen. So that's all I had. I'll be happy to take any comments or questions at my email address. Thanks for watching, and the code will be made available publicly, I understand. So thanks for watching, and I wish you a nice day.